All right, thanks everyone for coming. My name is Jason Gaitonde, and as he said, this talk is about our paper, Adversarial Perturbations of Opinion Dynamics and Networks, and this is joint work with John Kleinberg and Eva Tardos. So kind of the main insight underlying opinion dynamics and networks is the following. People's opinions are fundamentally affected by their interactions with other people. When you interact with your neighbors or friends or colleagues and share your opinions will tend to evolve as a result of these interactions. And there's been many models studied in the CS community and the social science literature that kind of hope to explain this. And a common feature of these models is that typically it'll have agents holding some sort of numerical opinion that'll be iteratively updated through some sort of graph dynamics. So probably the most famous and kind of simplest model of this is the de Groot model, which dates back 50 years or so. And in this one, the way that agents will update their opinions is they're going to just take the average of their graph neighbors. In this work, we'll actually be studying a variant of this model, which is called the Friedkin-Johnsen model. This model allows for agents to kind of hold innate priors. And I'll get into the formal specifications a bit later. And there's many other models, but that's the one we'll be focusing on. And within this Friedkin-Johnsen dynamics, there's been a lot of work on sort of considering interventions in these dynamics. There's many natural algorithmic questions on how to intervene in this process towards some sort of goal. There's been a lot of recent work on this, so just to kind of give you a flavor, for instance, the work of Gionis et al. From 2013 considers the problem of how to kind of unidirectionally shift opinions in one direction when you know that these dynamics are going to occur. So in this kind of line of literature, what we're going to be interested in is kind of giving more theoretical understanding to a very recent phenomenon that's become quite famous, which is that external adversaries trying to sort of cause disorder in a network. So this has been very prominent in political campaigns recently, times of civil unrest, and even though it's become more famous now, even back to 2009, for instance, the US was issuing reports that was kind of considering its own ability to conduct these sorts of activities, as well as their ability to defend against them. And this is an interesting objective, and it's a little different than the one I just talked from previous work. And this kind of objective leads to different and interesting kinds of behavior. For instance, on Facebook, some of these groups, what they would do is actually they would make an event for some sort of protest on an issue, while also through a different alias, they'd kind of schedule a counter protest at the same time to sort of artificially inflate this kind of disagreement. So the main point of this work is to kind of give some theoretical backing behind this. And the main kind of theme of this talk will be to consider the relationship between graph structure, these opinion dynamics, and the Friedkin-Johnsen dynamics, and how much power an adversary has to actually sow discord. So before getting into the formulas, I just want to give a quick sort of example of how these dynamics work. So the white nodes here are going to be nodes in a graph, and they're connected via these thick edges to other nodes. And as I said, opinions are going to be modeled as just real numbers. You should think of these as opinions on a political spectrum, say. Each node will actually also be connected to these gray nodes here, which will represent innate opinions, which you should think of as priors. And at the beginning of the dynamics, the initial opinions that each node has is going to equal their innate opinion. And then the agents will do a sort of these updates. And the way they do updates is they're going to take weighted averages of their innate opinion and their graph neighbors. So for instance, focusing on this, this node that I highlighted in green, it'll take, and I put the neighborhood in green as well, it'll look at these numbers, and it'll take the weighted average of them. Here, it will actually just take an unweighted average. You can check that this will cause the opinion to update to 1. And at the same time, all nodes on the graph will do this. But the key is actually that the innate opinions will stay fixed to their initial value. And then we repeat this process, and you can repeat it infinitely often, and then you'll reach convergence in the limit to these blue numbers. You can check that they are fixed points of the dynamics. So there's no further updating. And these will be the final opinions in the Friedkin-Johnsen dynamics. One thing I want to highlight for you right now is that there's kind of a duality in the role that edges plays. So the edges of the graph on the one hand will actually smooth out opinions. So you can see on this red edge that I highlighted, The initial opinions, or the innate opinions, were 2 and -1, which has a gap of 3. And at the end of this process, the opinions have gotten considerably closer. So on the one hand, the graph serves to kind of smooth out the innate opinions. But on the other hand, at the end of this process with these final opinions, they're also a source of tension between neighbors. For instance, we're going to be interested a lot in the square difference along the edges. And here you can check that this is 4/9 on this edge. So with this example in mind, here's like a bit more formally how this model works. We're going to fix an undirected graph G with possibly weights and with an adjacency matrix A. And as I said, we're going to model each person's initial opinions as numbers SI that are real numbers. And then the way the dynamics work is these formulas just give in math what I said in words, is that these updates are going to be by taking the weighted average of the neighbors and the innate opinions. And the weight on the innate opinions will be 1 in the standard formulation of this. So in the example I gave before, that gray node with the red 0, that'll be the SI of that node. And at the end of this process, this 1430, will be the final limiting values. And it's known that there's a nice analytic formulation of what those ZIs are in terms of the SI. Namely, the final opinions in the limit are this expression, Z equals I plus L, where inverse times S, where I is the identity matrix, and L is the graph Laplacian matrix, which is equal to the diagonal degree matrix minus the adjacency matrix. So the problem set up for us, again, we're interested in sort of how much conflict can an adversary cause in a network. The way we'll kind of model this is, suppose initially that the society is at a consensus, and without loss of generality, suppose they're a consensus at 0. Then an adversary's goal will be to actually induce discord by perturbing the innate opinions in some ball of a fixed radius R. And they'll do this, via ads or bots or a misinformation campaign. And you should think of this radius as kind of representing the limited power of the adversary, because these things take resources to do. And then once the adversary kind of perturbs these priors, the seeded opinions will evolve via the Friedkin-Johnsen dynamics to the expression I mentioned before. And the adversary's objective will be to do this to sort of maximize some measure of final discord. We'll consider a couple different ones, but they'll tend to be related to these square differences on edges, which we'll show can often be done via a quadratic form in L. So a bit more formally, the optimization problem for the adversary becomes this following expression, where they're taking the maximum over vectors of some bounded length of this expression, S transpose I plus L inverse, times some matrix F of L times that same I plus L inverse S, where F of L will be some quadratic form modeling the sort of physical discord we're interested in. And again, we'll give examples of those. And so many of you in the audience will probably see that an initial consequence of this is that the adversary's ability to induce discord is determined by the eigenvectors and eigenvalues of this matrix. Namely, the power that they'll have will be related to the top eigenvalue, and the optimizer of this will be the corresponding eigenvector. And this is a consequence of the Courant-Fisher min-max principle. So let's kind of see how this works. So consider an adversary that's interested in maximizing disagreement. And as I said, disagreement will be sort of the sum of weighted squared differences along the edges of the final opinions. In that framework that I just mentioned, this is attained very easily by setting F of L, the quadratic form, to just equal L itself. And an initial consequence of this is that one can show that for any graph, an adversary can cause at most R squared over 4 disagreement. And one thing to notice about this is actually a bound that's independent of the size of the graph. And again, the way you would show this is just to look at the eigenvalues and eigenvectors of this expression and find the maximizing eigenvector of this. And let's actually go into this a little bit deeper. So again, the question is sort of what are the eigenvalues of this matrix? And the way to do that is consider the following function. Q of x equals x over 1 plus x squared. The way you get that is by taking that matrix expression and just plugging in a variable x in for the L's. And so what happens is the eigenvalues of L just pass through this function. And just analytically, it's not too hard to show that the maximum of this function is attained at x equals 1 with a value of 1/4. So in this graph, we can plot the eigenvalues of L. Here, they're sort of the red dots. And then the eigenvalues of that matrix we care about will pass through this function, and they'll have the same eigenvectors. So the adversary is going to pick, as the way to kind of optimally do this, the eigenvector corresponding to the eigenvalue of L that gets maximized in this expression. Here, the one that they'd pick is actually to the largest eigenvalue of L. But as you can imagine that, as you shift the balance between innate opinions and how much weight that the agents place on their sort of graph interactions, this kind of balance will change. So suppose that actually agents start putting a lot more weight on their graph interactions. This can be attained, for instance, by shifting up to 5 times the Laplacian matrix. And then what the adversary is again going to do is look at which eigenvalue and corresponding eigenvector of L gets maximized in this sense. And then in this case, the new largest eigenvalue is attained at the eigenvector for lambda 3, so which is the second largest eigenvalue. And again, as I keep pushing this, and the weight gets higher on the Laplacian matrix, then the lambda 2 will be the eigenvalue and corresponding eigenvector that the adversary chooses. So this sort of says that the optimal adversary strategy in this simple setting is just to align their perturbation with the eigenvector of L, whose eigenvalue maximizes this expression. So sort of a main takeaway of this is actually that any eigenvector or eigenvalue of L can control the adversary's power for this objective, not just the extreme ones. And indeed, as I kind of said, as this balance shifts between how much weight people put on their innate opinions versus graph opinions, every non-trivial eigenvector of L will be an optimizer at some point. And to kind of compare this with the usual morals of spectral graph theory, kind of the smallest eigenvalues and eigenvectors physically kind of means something like the sparsest cut, whereas the largest eigenvalues have the physical meaning of kind of max cuts. This connection is very well studied, and those tend to be the eigenvalues and eigenvectors that have the most physical significance. And what we're kind of saying here is as the balance between how much weight you put on innate opinions versus the graph opinions changes, you kind of interpolate between the adversary strategy will kind of interpolate between these two things, passing through every eigenvector of L. We also study other forms of discord. For instance, we consider a form of repeated disagreement, which is, so kind of an example of how this would happen is, suppose that you take the final opinions of, say, the 2016 US election, and then let those become the new innate opinions for the next election cycle, at which point the dynamics will take place again, and then repeat this cycle. An adversary that's interested in kind of maximizing this form of disagreement in an infinite horizon, we have a similar bound on how much they can actually do. But in this setting, actually, it's controlled only by the second smallest eigenvalue or an eigenvector of L. And a very simple corollary of this is that actually for this objective, the complete graph is most robust to this repeated disagreement, subject to normalization constraints. We also consider a form of the sort of hybrid measure of polarization and disagreement that was considered in previous works. And we find very similar results, which is namely that only the second smallest eigenvalue and eigenvector actually end up mattering. And in this one, I also want to mention some independent work from this year from Chen and Raz that study a similar form of this problem via sparsity constraint adversaries. And they do this via primarily more combinatorial and non-spectral methods. But on the positive side, we also kind of consider the problem of defending the network. Namely, we consider how could a network defender sort of insulate a network from these sorts of attacks, knowing that an adversary will try and maximize discord. So the kind of setup we consider is, suppose that a defender has some sort of budget constraint, and what they're allowed to do is choose weights so that the adversary now must optimize respect to this sort of weighted norm. And the interpretation of this is that a network defender can kind of insulate nodes via online awareness training or removal of targeted ads to make it such that an adversary to perturb different nodes must pay more for some nodes than other nodes. And what we show is that for in a pretty flexible set of scenarios, you can actually compute the optimal weights via convex programming. So now, kind of the morals of the previous things was, again, I mentioned kind of this tension between how edges play two roles between, both smoothing opinions and also measuring disagreement. And kind of the moral was that, these things kind of balance out. But one can consider generalizations of this. And, what we were doing before is we were saying the same graph is dictating both the dynamics and sort of the measure of disagreement. But you can ask what happens when these are decoupled. For instance, you might think that opinion dynamics are going to be driven by an online network, through your social media interactions. But say an adversary knows this, but is actually interested in maximizing, say, the real world discord, say the discord between physical neighbors. So just kind of in pictures, you might think that this graph on the left, which is kind of like, the social media network, is how people kind of form their opinions. But the adversary is actually interested in maximizing disagreement on this graph on the right, which is sort of your physical connections with other people, your neighbors, and so on. So now we're going to consider two different graphs and let L be the opinion dynamics Laplacian and M be the Laplacian of sort of the measurement graph that the adversary cares about. And sort of the intuition is that, when L and M are the same, that might be sort of the best case scenario, and that the adversary has much less power. In this case, when they're decoupled, you might think that maybe, the adversary's power will necessarily grow by a lot. But we show actually that, this intuition isn't entirely correct. There are simple examples where the measurement Laplacian and the opinion dynamics Laplacian change, for instance, in these two. And somehow, even though the opinions dynamics and the disagreement measurement get decoupled, the adversary's power actually ends up decreasing in this case. Nonetheless, what one can show is that intuition that, something good is going on, the adversary is somehow, restricted when the graphs are the same, that intuition is kind of right. Namely, if two graphs have numerically similar spectra, one can show that the adversary's power actually cannot decrease by very much. And sort of the reason for this is that L and I plus L inverse, which is what was kind of popping up before, are going to be maximally spectrally misaligned. But what one can kind of show in the relationship between the two graphs is that what matters in determining whether an adversary's power will increase or not is spectral similarity. And indeed, seminal results of Batson, Spielman, Srivastava have shown that every graph has a sparse spectral approximator. And one can show that if the two graphs are spectral approximators of each other, the adversary's power won't change by very much. So what that means is sort of the edge-by-edge physical similarity of the two graphs is sufficient for the adversary's power to not change much, but it's not necessary. And correspondingly, you can show that when the two graphs are kind of dissimilar spectrally, the adversary's power will greatly increase compared to the single graph setting. So just kind of summarize, the main theme of this talk is kind of what's the connection between graph structure and these dynamics and how much power an adversary has. And what we show is that the entire spectral structure can be relevant for certain objectives, but for others only extreme eigenvalues matter. And moving forward, there's a couple of interesting questions. For instance, more general types of adversaries. And I think something that's really interesting is kind of considering models with co-evolving graphs and opinions. For instance, the famous Hagelman-Krauss model. It'd be very interesting to see if people could extend these results to these kinds of models. And with that, that's all I have. Thanks so much.